We spend most of our lives, no matter how busy we are, thinking about whether life exists somewhere else out there. And most of the time, that thought leads to one place: Mars. Mars has no forests, no oceans, no clouds, but a team of scientists just looked at what is inside its ancient rock, and what they found, they could not explain without considering life. You have seen the photos from Curiosity, from Perseverance, from China's Zhurong rover. The more you look, the harder it becomes to ignore the question, why does this dead planet look so familiar? Just this February 2026, they ran the math, and every non-biological explanation they tested failed. Meteorites, atmosphere, space dust, all of them gone. One answer survived. We are going to walk through exactly what they found: the molecules, the math, the elimination of every alternative, and the one hypothesis left standing when the dust settled. Take a breath. The debate just shifted forever. Here is what we know. In February 2026, a team of scientists published a peer-reviewed study in one of the most respected journals in astrobiology. They had taken an ancient Martian rock sample, applied a new analytical technique, and run the numbers on what came back. The result was this: long-chain organic molecules were present inside the rock at concentrations that no known non-biological process on Mars can explain. Every alternative was tested. Every alternative failed. The biological hypothesis was the last explanation standing. That is the finding. That is what this video is about. The molecules are called alkanes, long chains of carbon and hydrogen, 10, 11, and 12 carbon atoms linked in a row. On Earth, chains this length almost always come from one place: living cells. When a cell dies and its membrane breaks down, these are the molecules left behind. Confirmed chemistry, well understood, reliable, finding them on Mars. In these quantities, inside a sealed 3 billion-year-old rock, is what stopped the team cold. Now, here is the number that puts the finding in perspective. The team measured 30 to 50 parts per billion of these molecules in the sample today. That sounds like almost nothing, and it is. But that tiny trace is not the original amount. It is what survived after 80 million years of Mars doing everything in its power to destroy it. Using a standard radiation decay calculation, verified by 3 independent atomic measurements inside the rock itself, the team worked backwards. What was the original concentration before 80 million years of destruction began? The answer came back between 120 and 7,700 parts per million. That range falls squarely within what ancient biological lakes on Earth actually produced. It matches the chemistry of microbial life. It does not match meteorites. It does not match space dust. It does not match the ancient atmosphere. It does not match underground chemistry at the site. The team published that honestly. One non-biological option remained that could not be fully ruled out, but it also could not be calculated. It was a possibility with no numbers behind it. So the question this video walks through is not whether the finding is real, it is confirmed. The question is how they got there. What rock, what technique, what calculation, what elimination process produced a result that the scientific community cannot currently explain away? To understand what was found, you need to understand where it was found. And the place this story starts is a lake on Mars that dried up 3 billion years ago. What that lake looked like, what it preserved, and why it matters, is where the story of this discovery truly begins. Scientists hope this discovery is a new beginning, not a final answer, a door opening onto something much larger. And to understand why they feel that way, you need to understand the rock that started it all, what it looked like, what it was, and what it tells us about a Mars that no longer exists. The finding came from a rock called Cumberland. Not a dramatic name, not a famous place, just a patch of grey mudstone at the bottom of what was once a calm, shallow lake inside a crater on Mars. Fine grey powder, the kind you might find at the bottom of any dried-up lake on Earth. Unremarkable to look at, extraordinary to analyse. Gale crater sits near the Martian equator. From orbit, it looks like a giant scar, roughly the size of Connecticut, carved into the surface by an ancient impact. Billions of years ago, water pooled inside it. For millions of years, that water sat still, slowly building up sediment layer by layer, the way lakes on Earth do today. That sediment hardened into mudstone. On Earth, mudstone is one of the best preservers of ancient biology we know. It traps organic molecules. It seals them away from oxygen, from heat, from the forces that normally erase biological evidence over time. Some of the oldest confirmed signs of life on Earth came out of mudstone. Scientists know this well, which is exactly why finding it on Mars made them pay very close attention. When the CuriosityRover analysed Cumberland, it found clay minerals, the kind that only form in neutral, non-acidic water. Water a human could theoretically drink. Confirmed. It found nitrates, which are nutrients. It found sulfur compounds that help lock organic molecules in place over geological timescales. It found carbon. Lots of carbon. Scientists were already excited before the long-chain molecules were ever discovered. Cumberland looked, chemically speaking, like exactly the kind of place where life gets started. Warm, wet, nutrient-rich, stable for millions of years. Now, here is what makes this genuinely personal. 3,700,000,000 years ago, when water was pooling in Gale crater on Mars, something remarkably similar was happening on Earth. It was the Archean Eon. The earliest microbial life on our planet was just beginning to take hold. Single-celled organisms living in shallow lakes, building cell membranes out of fatty acids, leaving chemical fingerprints in sediments that we still find today. The ages match almost exactly. Whatever produced those organic molecules in Cumberland, if something produced them, was doing it at the same moment life was waking up on Earth, 400 million miles away. That is either a coincidence, or it is something far more significant than a coincidence. But to understand the finding, you need to understand why the molecules inside Cumberland almost never got found at all. The technique that unlocked them did not exist when the rock was first drilled, and the gap between collection and discovery is one of the most important parts of this entire story. To understand the finding, you also need to understand the molecule, because the type of organic compound matters as much as the quantity, and the specific molecules found in Cumberland carry a chemical fingerprint that points in a very specific direction. That fingerprint is the next piece of this story. The rock was drilled in 2013. The CuriosityRover was crawling across the ancient lake bed in Gale crater. It stopped, extended its drill arm, and bored a small hole into Cumberland, a rock that had been sitting untouched for 3 billion years. The rover collected the powder, ran it through its onboard chemistry lab, and found some organic molecules. Shorter ones, less informative ones. Scientists published the results, noted the habitable chemistry, and moved on. The long-chain molecules, the ones that would change everything, were in that same sample the whole time. They were just invisible to the technique being used. Here is why. The chemistry lab on Curiosity is extraordinary. Think of it as a miniature science lab the size of a microwave, operating in temperatures cold enough to freeze your lungs in seconds. It can heat rock samples, separate their molecules, and identify what is inside. Remarkable technology. But its default settings were calibrated for shorter, lighter molecules, the kind scientists expected to find. Long-chain molecules need something different. To free them from the rock, scientists had to preheat samples to over 2,000 degrees Fahrenheit. That technique was developed after Curiosity was already on Mars. It was refined to search for amino acids. Nobody designed it to look for what it found. When scientists finally applied it to the Cumberland sample, they were running a different experiment entirely. What came back was unexpected. Long chains of carbon and hydrogen. 10, 11, 12 carbons linked in a row. The largest discrete organic molecules ever found on the surface of Mars, sitting in a sample that had been archived for 12 years. And here is what that means for every other sample ever collected on Mars. Every rock drilled under the old default settings, every instrument run at standard temperatures, may have been systematically blind to this entire class of molecules, not because the molecules were absent, because no one was looking with the right technique. Curiosity has drilled dozens of samples across Gale crater. Perseverance has cored over 2 dozen at a separate crater hundreds of miles away. If this technique was not applied to those earlier samples, how many of them are hiding the same signal right now? Scientists are now asking exactly that question. Multiple research teams have begun reanalyzing archived data. The most significant organic chemistry finding in Mars exploration history came from re-examining a 12-year-old sample with a tool that did not exist when the sample was collected. One technique, one archived rock, one result that rewrites the search rules for every mission that follows. But the finding is only as strong as the math behind it. And the math is where this story gets genuinely hard to set aside. One technique, one archived rock, one result that rewrites the search rules for every mission that follows. But the finding is only as strong as the math behind it. And the math behind it is where this story gets genuinely impossible to set aside, because the calculation that revealed the original abundance is the calculation that eliminated every conventional explanation for what was inside that rock. 30 to 50 parts per billion. That is what Curiosity measured in the Cumberland sample. 1 part per billion is roughly 1 drop of ink in an Olympic swimming pool. The signal was barely there. In isolation, it would be easy to dismiss. But that number is not the original amount. It is the survivor. Mars has no magnetic field. Earth does. And that invisible shield deflects the constant stream of high-energy cosmic particles flying through space. Mars lost its equivalent of that shield roughly 4 billion years ago. Ever since, galactic cosmic rays have been hitting the Martian surface with nothing to stop them. They penetrate deep into rock and destroy organic molecules through a process called radiolysis. High-energy particles slam into chemical bonds and break them apart. Given enough time, even the most stable organic compounds get reduced to fragments. This is confirmed. This is exactly what happened to Cumberland. 3 independent measurements of rare atoms created inside the rock by cosmic ray impacts all point to the same answer. The mudstone has been exposed on the Martian surface for roughly 80 million years. 3 separate atomic clocks. Same result. And the dose rate was measured directly by the CuriosityRover during its time on Mars. The team used a standard radiation decay law, the same mathematical relationship used to date fossils and calculate how long organic molecules survive in space. They plugged in the current abundance, the confirmed radiation dose, and the most conservative decay constant available, one measured for a molecule known to break down more slowly than alkanes. The answer came back between 120 and 7,700 parts per million. Curiosity measured 30 to 50 parts per billion today. The original concentration was up to 100,000 times higher. The radiation nearly erased it entirely. That number is more organic material than has ever been found in any Martian meteorite. More than volcanic rock processes on Mars are known to produce, more than space dust delivers, more than the ancient atmosphere could have deposited. The team stated it clearly in their paper. The result is inconsistent with currently accepted non-biological explanations. Every known, non-living source was about to face that number, and one by one, starting with the most intuitive suspect of all, they were going to fail. The elimination process is where the scientific weight of this finding becomes impossible to ignore. And it starts with the explanation every scientist would have preferred to be true. Every known non-living source was about to face that number, and one by one, starting with the most intuitive suspect of all, they were going to fail. The elimination process is where the scientific weight of this finding becomes impossible to ignore, and it starts with the explanation every scientist would have preferred to be true. The quantity was extraordinary, but the identity is what sealed the case. Every cell in your body is wrapped in a membrane. That membrane is built largely from fatty acids, long chains of carbon and hydrogen, linked together like beads on a string, folded into a barrier that separates the inside of a living cell from everything outside it. Without fatty acids, there are no membranes. Without membranes, there are no cells. Without cells, there is no life as we know it. Alkanes are what fatty acids leave behind when they die. When a cell breaks down, when heat or pressure or time degrades its fatty acids, the molecules lose a small fragment and become alkanes. Shorter, simpler, but still recognizable. They still carry the structural signature of what they once were. Forensic chemists on Earth use this relationship to identify biological material in ancient rocks, find the alkanes, trace them back to their fatty acid parents, and you have found chemical evidence that something was once alive. That is the technique, that is the logic, and it works reliably. The alkanes Curiosity found in Cumberland had carbon chains of 10, 11, and 12 atoms. On Earth, chains this length are almost exclusively biological. Chemistry without life tends to produce shorter, simpler molecules. The longer the chain, the harder it is to build without biology doing the work. Think of it like handwriting. Short, random lines can appear by chance. A full signature, with specific loops and lengths and patterns, is almost impossible to produce by accident. A 12-carbon alkane chain on Mars is starting to look like a signature. That is a theory, not yet confirmed, but it is grounded in chemistry we understand extremely well. And here is the double problem this creates for every non-biological explanation. It is not enough to deliver the right quantity. A non-biological source also has to deliver the right type of molecule. Both tests have to be passed. Space dust fails the abundance test by a factor of 1 million. It also fails the identity test because dust-derived organics are dominated by short-chain fatty acids, the simpler, lighter molecules that form more easily in space without any biological help. Meteorites fail the abundance test completely. They also fail the identity test because fatty acids found in carbonaceous meteorites tend to be short chains, mostly under 7 carbons. The Cumberland molecules were 10, 11, and 12. Every non-biological candidate faced 2 questions: how much and what kind? None of them answered both. What produced the right quantity and the right molecular identity in a sealed 3-billion-year-old Martian rock is the question that has no clean non-biological answer, and the elimination of every candidate, one by one, is where this story goes next. What produced the right quantity and the right molecular identity in a sealed 3-billion-year-old Martian rock is the question that has no clean non-biological answer, and the elimination of every candidate, one by one, is where this story goes next. The first suspect was the most obvious one, and the way it failed tells you everything about how carefully this team did their work. Every day, Mars gets hit by space rocks, small ones mostly, dust-sized particles and fragments constantly raining down from the asteroid belt. Larger meteorites hit occasionally, carving the craters that cover the Martian surface. These space rocks carry organic molecules. Carbonaceous meteorites, some of the most chemically rich objects in the solar system, contain amino acids, fatty acids, and complex organic compounds. Scientists have studied them for decades, So the first question the team asked was logical. Could meteorites explain the organic abundance in Cumberland? The answer came back fast. No. Fine space dust, particles smaller than a human hair, rains down on Mars continuously. But fine particles cannot penetrate solid rock. They settle on the surface, mix into loose soil, and stay there. They cannot burrow 13 feet down into a mudstone that formed billions of years ago at the bottom of a lake. Any organics carried by space dust could only have entered Cumberland during the brief window before the rock hardened. After that, the rock was sealed. This is confirmed geology. The team calculated exactly how much organic material space dust could have contributed during that window. Using known estimates of the dust flux on Mars and the rate at which lake sediments accumulated in Gale crater, they arrived at a maximum possible contribution of about 0.1 parts per billion of alkanes. The original abundance calculated for Cumberland was at minimum 120 parts per million. 0.1 parts per billion against 120 parts per million. Space dust falls short by a factor of at least 1 million. 1 million times short. What about larger meteorites? Could a direct impact have delivered organics deep into the rock? The team checked. There is no evidence of any impact crater at the Cumberland location. The rock's formation age has not been disrupted by any large impactor. Confirmed. There is also a chemistry problem. Fatty acids found in carbonaceous meteorites tend to be short chains, mostly under 7 carbons long. The Cumberland alkanes had chains of 10, 11, and 12 carbons. The molecular fingerprint simply does not match. 2 failed tests on 2 separate measures. The abundance is wrong. The identity is wrong. Meteorites were the most intuitive explanation. The one scientists would have preferred, because it requires no extraordinary conclusions. The numbers eliminated them completely. One conventional explanation, gone. But scientists are thorough. There were still more suspects to test. And the next one came from the sky itself. An ancient Martian atmosphere that, billions of years ago, was thick enough to hold weather, warm enough to support liquid water, and complex enough to produce its own chemistry. Could that ancient sky have rained organic molecules down into the Cumberland lake bed? The chemistry behind the answer is fascinating, and the way this explanation fails is completely unexpected. Space dust deserves its own moment in the investigation. Interplanetary dust particles, the microscopic rain of space material falling onto planetary surfaces constantly, were taken seriously enough by the team to model in full detail. And the way they failed reveals something important about how isolated and self-contained the organic chemistry in Cumberland actually was. These particles are everywhere in the inner solar system. Every planet, every moon, every asteroid is constantly being dusted from above. On Earth, roughly 40,000 tons of this material falls every single year. On Mars, the rate is lower, but still substantial. Scientists have studied these particles by collecting them in Earth's upper atmosphere using high-altitude aircraft. They are genuinely rich in chemistry. They carry amino acids, simple hydrocarbons, and fatty acid precursors that form through natural reactions in space. For decades, interplanetary dust was considered a serious and plausible source of organic molecules on planetary surfaces. Scientists built it into their models. They factored it into their estimates. It seemed reasonable. Cumberland ended that idea. The team calculated the maximum possible contribution of these particles to the Cumberland sample during the period when the lake sediment was forming. They accounted for the flux rate on Mars, the rate of sediment accumulation in Gale crater, and the fraction of dust mass that is actually organic. They assumed the most generous possible numbers at every step, giving space dust every advantage. The result was a maximum contribution of about 0.1 parts per billion of alkanes, the same ceiling as meteorites, because neither source can penetrate solid rock after it has already formed. Against a calculated original abundance of up to 7,700 parts per million, that contribution barely registers at all. It is the equivalent of trying to explain an ocean by pointing at a single raindrop that fell once, briefly, on a completely different continent. But here is the detail that makes this failure even more complete. The specific types of organic molecules delivered by space dust do not match what was found in Cumberland. Dust-derived organics are dominated by short-chain fatty acids, the simpler, lighter molecules that form more easily in space chemistry without any biological help. The Cumberland alkanes were long-chain, heavier, more complex, much harder to build without something doing deliberate molecular assembly. Space dust did not just fail the abundance test, it failed the identity test too. 2 separate failures on 2 separate measures, 2 suspects fully eliminated. Every straightforward, reach for the obvious explanation had been put to the math and found severely lacking. The non-biological case was in serious trouble, and the most complex alternatives had not even been tested yet. The ancient Martian atmosphere was next, and while it would also ultimately fail, the way it failed reveals something genuinely surprising about how different ancient Mars was. It begins with methane. It ends with a threshold that ancient Mars almost certainly never crossed. What that threshold is, and why it matters, is not what you would expect. 4 billion years ago, Mars had a real atmosphere, not the thin whisper of carbon dioxide that barely exists today, too weak to breathe, too thin to block radiation. Ancient Mars had pressure, warmth, weather. Scientists have confirmed it had an atmosphere thick enough to support liquid water on its surface for millions of years. That is confirmed. On early Earth, the atmosphere produced something called organic haze. Sunlight hit methane molecules high up, broke them apart, and the fragments reassembled into complex organic particles that drifted slowly downward and settled into ancient sediments. Some scientists believe this process contributed significantly to the organic record found in Earth's oldest rocks. Could the same thing have happened on Mars? Could an ancient Martian haze have deposited enough organic material into the Cumberland lakebed to explain what the team calculated? The team ran the chemistry, and the Martian atmosphere failed before it even got to the abundance test. Here is why. To produce organic haze, an atmosphere needs a specific ratio of methane to carbon dioxide. Experiments confirm that ratio needs to exceed 1 to 10. Below that threshold, no meaningful haze forms at all. This is confirmed laboratory science. Early Mars almost certainly had carbon dioxide pressures between half a bar and 1 full bar. That is a substantial amount of carbon dioxide. For haze to form under those conditions, Mars would have needed methane concentrations of at least 5 to 10% of its entire atmosphere. The best estimates for ancient Martian methane put it somewhere between 10 and 100 parts per million under normal conditions. Even under the most extreme volcanic or hydrothermal scenarios, occasional spikes to perhaps 1%. That is still far below the threshold needed. Even generous assumptions fall far short. The atmosphere failed the chemistry test before the abundance test was even necessary. And here is the irony worth sitting with. The very carbon dioxide that makes the atmosphere fail as an organic source is what helped keep ancient Mars warm enough for liquid water to persist. Cumberland formed in that environment. The same conditions that eliminate the atmosphere as an explanation are the conditions that made the lakebed possible in the first place. The sky could not explain Cumberland, but the sky helped create the world where Cumberland formed. 3 explanations gone, the next suspect was underground, deeper, hotter, more chemically complex than anything tested so far, and it is the one explanation the team could not fully eliminate. Not because it works, but because it cannot be measured. And an explanation you cannot measure is a very specific kind of problem in science. What that means for the biological hypothesis is something the research community is still wrestling with right now. The underground option is the last door, and it is half open. Deep underground, rock and water do strange things together. When water gets hot enough, pressurized enough, and moves through the right minerals, it can trigger chemical reactions that build organic molecules from scratch. No life required. Just heat, pressure, water, and the right chemistry. Scientists call this hydrothermal synthesis. It happens on Earth today, at the bottom of oceans and deep in volcanic regions, confirmed. On early Mars, with its volcanic activity, its subsurface heat, and its abundant liquid water, hydrothermal systems almost certainly existed. The question is whether they could have produced enough long-chain alkanes, transported them to the Cumberland lakebed, and deposited them in concentrations high enough to match what the team calculated. This is the one non-biological explanation the team could not fully eliminate, and the reason why is critical to understand. Laboratory experiments have shown that under the right conditions, hydrothermal chemistry can produce long carbon chains. One study showed chains up to 21 carbons from reactions at high temperatures and pressures using cobalt and iron as catalysts. Another showed fatty acid chains up to 18 carbons forming with iron-rich minerals. The chemistry works in the lab. That is confirmed. The problem is the rock itself. Cumberland shows no signs of having experienced high temperatures. Analysis of its mineral content found none of the specific minerals that form when rock is heated by hydrothermal processes. Their complete absence suggests Cumberland never got hotter than about 140 to 170 degrees Fahrenheit. Warm enough for life, too cool for the synthesis reactions that produce long-chain organics in a lab. Confirmed geology. So, if hydrothermal reactions produced these molecules, they did it somewhere else entirely, far from Cumberland. And then the organics would have had to travel through ancient groundwater flowing underground across an unknown distance to be deposited in the lake. That is technically possible. Water does transport dissolved organic compounds. Ancient Martian groundwater systems were likely extensive, but nobody can quantify it. Nobody knows where the hypothetical source was. Nobody knows how efficient the transport would have been. Nobody knows how much would have survived the journey. The team was honest. They could not rule out hydrothermal transport, but they also could not calculate it. The unknowns are too large. An explanation that cannot be measured is not really an explanation. It is a possibility, an open door. And when 3 explanations have been fully eliminated, and the one remaining non-biological option is an unquantifiable unknown, the next hypothesis on the list becomes very difficult to step around. What would an ancient Martian biosphere have looked like? And when you run the numbers, do they actually fit? The answer to that second question is what makes scientists quietly hopeful in a way they rarely allow themselves to be. Because the numbers do not just fit, they match closely, and that kind of match is what begins a new chapter in science. Let's be precise about what the team actually claimed. They did not say they found life on Mars. They said, in the careful language of peer-reviewed science, that it is not unreasonable to hypothesize that an ancient Martian biosphere could have produced the organic concentrations found in Cumberland. In science, that is a significant statement. It means the data survived scrutiny and the biological option cannot be dismissed. So what would that biosphere have looked like? Start with what we know. 3 to 4 billion years ago, Gale crater held a lake with neutral water, nitrates, sulfur compounds, carbon, and clay minerals that form only in stable, long-lasting aquatic environments. The temperature was moderate. The chemistry was what multiple independent research teams have described as habitable. That is confirmed. On Earth, those conditions match exactly the environments where the earliest microbial life thrived during the Archean Eon. Single-celled organisms living without oxygen, drawing energy from chemical reactions between minerals and water. Their cell membranes were made of fatty acids. When they died, those fatty acids settled into lake sediments and were preserved in mudstone for billions of years. The team compared Cumberland's estimated original organic concentration directly against what ancient Earth lake sediments actually contain. Modern lake sediments from productive environments contain up to tens of parts per million of fatty acids. The Black Sea holds around 200 parts per million in fresh surface sediments. Some ancient geological formations on Earth hold thousands of parts per million of preserved hydrocarbons. Cumberland's estimated range of 120 to 7,700 parts per million falls squarely within the range of what biological productivity on early Earth actually produced. The numbers match, and here is what makes this genuinely hard to set aside. The Perseverance rover, 300 miles away in a completely separate crater, independently found organic material in mudstones with mineral associations that on Earth are produced almost exclusively by microbial metabolism. 2 rovers, 2 separate locations, 2 independent research teams, both pointing in the same direction. The team also noted the timing. Whatever biological processes could have produced these organics on Mars would have been active approximately 3,700,000,000 years ago. On Earth, the microbial processes that produce similar fatty acid signatures were becoming established at almost exactly the same time. 2 neighboring planets, same era, same chemistry, same organic signatures. That is either the most remarkable coincidence in the history of science, or it is the beginning of the most hopeful answer humanity has ever found. The possibility that life is not a miracle, that it is a pattern, that wherever the conditions are right, something reaches toward existence. Scientists are careful with hope, but this is the finding that is making them allow it. The molecules in Cumberland almost never got found. Not because they were missing, not because the science was wrong, but because the technique used to find them was invented years after the rover landed. It was designed for a completely different purpose, and nobody knew it would unlock the most significant organic chemistry finding in Mars exploration history. The chemistry lab on Curiosity is extraordinary by any measure, but its default settings were calibrated for a specific range of molecules. Shorter ones, lighter ones, the kind scientists expected to find based on everything they knew at the time of launch. Long-chain molecules, like the ones in Cumberland, need something different. To free them from the rock matrix, scientists had to preheat samples to over 2,000 degrees Fahrenheit. That technique was approved for use on Curiosity after the rover was already on Mars. It was refined specifically to enhance the search for amino acids. Nobody had long-chain alkanes on their original list. The search for those molecules was not even part of the mission design. When scientists applied it to the Cumberland sample, they were running a different experiment with a different goal. What they found was entirely unexpected, and here is what that tells us about every Mars mission that came before. Every sample analyzed under the old default settings, every instrument run at standard temperatures, may have been systematically blind to this entire class of molecules. Not because the molecules were absent, because no one was looking with the right procedure. Curiosity has drilled dozens of samples across Gale crater alone. The Perseverance rover has cored over 24 samples at a separate crater hundreds of miles away. If this higher temperature technique was not applied to those earlier samples, how many of them might be hiding the same signal right now, waiting in a database somewhere? The scientists are now asking that exact question. Multiple research teams have begun systematic reanalyses of archived data from earlier missions, going back through years of stored results with fresh eyes and updated methods, not because they expect to find something specific, because this discovery proved that the possibility is real. The most significant organic chemistry discovery in Mars exploration came from reanalyzing a 12-year-old sample using a technique that did not exist when the sample was collected. The breakthrough was not a new mission. It was a new lens pointed at old data, one accidental methodology, one archived dataset, one result that rewrites the search protocol for every mission that follows. But why did the sample sit unanalyzed for over a decade in the first place? The answer is not a failure. It is actually the standard pace of planetary science, and understanding that pace reveals something important about where the next discovery might already be sitting right now. The 12-year gap between collection and discovery is not the exception in this field. It might very well be the rule. The data existed in 2013. The Cumberland sample was drilled, analyzed, and filed. Scientists published findings about its minerals, its nutrients, its habitable chemistry. Papers were written. Press releases went out. The world registered it briefly. Mars had a wet past. Then the news cycle moved on, but the long-chain molecule data was buried in there the whole time, hidden inside raw instrument outputs that nobody had yet processed with the high-temperature technique, because that technique was still being refined, tested, and formally approved for use. The data sat in storage, correct and complete, invisible to anyone who did not yet have the right key to read it. 12 years passed. In planetary science, 12 years is not unusual. It might even be considered fast. Mars missions operate on timescales that would seem absurd in almost any other field. Curiosity launched in 2011, landed in 2012, and is still actively driving across the Martian surface today, more than a decade past its original 2-year design life. The data it generates accumulates faster than teams of scientists can fully analyze it. The scientific backlog on Mars data alone is immense, but the gap between sample collection and this particular discovery carries a specific lesson that the research team highlighted directly in their published paper. When Cumberland was first analyzed, the organic compounds found were shorter and less informative than what a higher temperature analysis would later reveal. Scientists noted those early results, published them, and moved forward. The possibility that deeper chemistry was hiding in the same sample was simply not on anyone's radar yet. The team that made this discovery did not drill a new hole. They reanalyzed an old one, using a method developed after the original analysis, applied to archived data from a mission that everyone had already celebrated as a success. That is what makes this discovery significant, beyond the chemistry itself. The most important organic chemistry finding in Mars exploration history was sitting in a computer database for over a decade. Waiting, patient, unchanged. How many other datasets hold findings like this? How many other archived samples from Curiosity, from Perseverance, from rover missions not yet launched, will eventually yield discoveries that nobody anticipated when the data was first collected? The answer, based on this precedent, is almost certainly more than anyone currently suspects. And that answer changes how planetary scientists think about their archives. Multiple research teams have already begun reviewing older datasets with updated methods. The universe does not always announce its secrets the first time they are recorded. Sometimes the data and the method to read it arrive years apart, waiting for someone to connect them. When they finally connected here, the result changed what scientists thought they knew about the organic inventory of an entire planet. And that inventory, as it turns out, is not just sitting in one crater. Curiosity was not alone in pointing this direction. 300 miles northeast of Gale crater, the Perseverance rover has been exploring Jezero crater since 2021. Jezero is different from Gale. It has a preserved river delta, clear evidence that water once flowed into it from outside the crater. Scientists consider it one of the most promising sites on Mars for ancient biosignature detection. In 2022, Perseverance detected aromatic organic compounds in mudstone at the base of the delta, confirmed. Then in 2023, the team found organic molecules in carbonate rocks in a different part of the same crater, also confirmed. Both detections were in sedimentary rock. Both were associated with minerals that, on Earth, are almost always produced by biological activity. The team that published the Cumberland analysis in February 2026 mentioned the Perseverance findings directly, not as proof, but as independent corroboration of a pattern. 2 rovers, 2 craters, 2 research teams working separately, both finding organic molecules in ancient Martian mudstone in quantities and chemical contexts that require explanation. In science, a single finding can always be explained away. Instrument error, contamination, a local quirk in the geology. But 2 independent data points pointing in the same direction are something different. They suggest a pattern, and patterns are what science runs on. The specific mineral associations at Jezero matter here. On Earth, the carbonate minerals found alongside those organic detections are often produced by microbial activity in carbonate-rich environments. Microbes alter the chemistry of their surroundings. They leave mineral fingerprints as distinctive as their molecular ones. The pattern at Jezero is not proof of biology, but on Earth it would send a geologist directly to the site with sample jars and very focused attention. Think of it like arriving at a scene and finding one footprint, interesting, then finding a second footprint, same size, same shape, in a completely separate location. Now, you are not looking at a coincidence. You are looking for a source. The question is whether the instruments currently on Mars can tell us what that source was. And the answer, unfortunately, is almost certainly not. Understanding why leads directly to the most frustrating reality in this entire investigation. The tools that could definitively settle this question already exist. They work reliably. They are used routinely on Earth to identify biological material in ancient rocks billions of years old. They are just sitting on the wrong planet. The evidence has been assembled across 2 craters by 2 rovers, analysed by multiple independent teams, all pointing in the same direction. What remains is verification. And verification requires something that does not yet exist on the Martian surface. 2 rovers, 2 planets worth of chemistry pointing the same way, and no instrument currently on Mars capable of telling us definitively what produced any of it. The gap between the evidence and the answer is not scientific, it is logistical. And logistical problems have solutions if someone chooses to fund them. The next chapter is about exactly that funding fight. There is a problem with everything described so far. Every detection, every calculation, every comparison to Earth biology. All of it depends on instruments the size of a microwave, built to survive a rocket launch, operated remotely across hundreds of millions of miles of space with a communication delay that makes real-time experiments impossible. The chemistry lab on Curiosity is extraordinary, but it cannot do what a laboratory on Earth can do. It cannot isolate individual molecules and measure their precise structure. It cannot run the combination of tests that would definitively distinguish biological from non-biological origin. The single most powerful tool for confirming biological origin in ancient organic molecules is called compound-specific isotope analysis. Here is the core idea. All carbon atoms come in slightly different versions, mostly carbon-12 and carbon-13. These behave identically in everyday chemistry, but living things preferentially use the lighter version when building their molecules. The ratio of light to heavy carbon in biologically produced organics is measurably different from organics produced by geological processes, and that signature survives in rock for billions of years. Scientists have used this exact test to verify biological material in rocks over 3 billion years old here on Earth. It is reliable, it is well understood. For the Cumberland molecules, a strongly biological reading would be powerful evidence. A non-biological reading would argue strongly against life. It is as close to a yes or no test as chemistry gets. The instrument required is standard equipment in any geochemistry lab on Earth, about the size of a kitchen appliance. Scientists use it routinely. Getting it to Mars? making it operate in Martian conditions, and running it on a specific sample requires either a mission built specifically around that instrument, or something simpler in concept but enormously difficult in practice. Bringing the Martian samples to Earth, Perseverance is collecting rock cores for exactly this purpose. Each sample is sealed in a titanium tube, documented with extraordinary care, and cached on the Martian surface. The plan is to retrieve those tubes and return them to Earth, where laboratories around the world would run every available test on actual Martian rock. The results could be definitive, not suggestive, definitive. But that mission is in serious trouble, and understanding what is happening to it explains why the February 2026 discovery is not just a scientific finding. It is also a political argument being made at exactly the right moment. The mission designed to answer this question is fighting for its life right now, and the window to act is not open forever. The mission designed to answer this question is fighting for its life right now, and understanding that fight and what the scientific community is doing to win it is where this story moves next. Because the argument being made in those budget meetings is not just about money. It is about whether humanity chooses to answer this question in our lifetime. For a moment, it looked like the samples might never come home. Mars Sample Return, the mission designed to retrieve the cores Perseverance has been collecting and bring them back to Earth, hit a serious crisis in 2024. An independent review board found the original mission design was too complex, too expensive, and significantly over budget. The projected cost had grown from around $4 billion to potentially $10 billion or more. The projected return date had slipped from 2031 to 2040 and possibly beyond. The review board was direct. The mission, as designed, was not executable. Something fundamental had to change. The scientific community responded with urgency. Hundreds of researchers explained publicly what those samples represent: the most carefully selected, most thoroughly documented Martian material in human history. Each core collected at a site chosen specifically because it showed signs of ancient habitability. Each tube sealed and labeled for the exact kind of analyses that could answer the life question definitively. Losing them or delaying their return by decades would set the search for Martian life back by a generation. Confirmed data sitting on another planet, inaccessible, is not science, it is storage. The mission is currently being redesigned. Multiple cheaper approaches are being evaluated, including options using commercial launch providers and simpler return vehicles. The outcome is not settled, but here is what changed when the Cumberland findings were published in February 2026, directly into the middle of this debate. When Mars life was an abstract possibility, the political case for spending $10 billion on sample retrieval was difficult. When the case is concrete, when scientists can point to specific molecules at specific concentrations in specific rocks and show that every non-biological explanation fails the math, the argument takes on a completely different weight. The timing is not accidental. The scientists who published this paper live in the world of funding and mission decisions. They know that evidence changes arguments. The samples exist right now, sitting in tubes on the Martian surface. The chemistry they contain may be the most scientifically significant material ever collected by humanity. Getting them back is a choice being made right now in budget meetings and political decisions that most people will never hear about. Scientists are hopeful, not blindly, but because the evidence built a case strong enough to fight for. And what those samples could reveal is a test so definitive that it would settle the question once and for all. That test has a name, and understanding it makes clear just how close we are to the most important answer in human history. And even beyond the mission funding, there is a deeper question worth sitting with. If the samples do come home and the tests are run and the answer turns out to be yes, what does that actually mean for every person alive when it happens? The practical and philosophical consequences of confirmation are something almost no one is talking about. But they reach much further than most people expect. Let's think clearly about what the biological hypothesis actually proposes. Not aliens, not complex creatures. The hypothesis for Cumberland is about microbes, single-celled organisms so small that billions of them would fit on the head of a pin. Organisms that, if they existed on early Mars, were almost certainly more primitive than anything alive on Earth today. Here is what the science supports as a reasonable model. 3 to 4 billion years ago, Gale crater held a lake with neutral water, moderate temperatures, and nutrients including nitrogen, phosphorus, sulfur, and carbon. All of this is confirmed. The chemistry matches what multiple independent research teams have called habitable. On early Earth, environments like this were colonized by anaerobic chemolithotrophs. That name sounds complicated. The concept is simple. Microbes that get energy not from sunlight, but from chemical reactions between minerals and water. They do not need oxygen. They do not need warmth beyond a basic range. They thrive in exactly the conditions Cumberland describes. These organisms build their cell membranes from fatty acids, long chains of carbon and hydrogen, folded into a barrier that separates the inside of a living cell from everything outside. When they die and their cells break down, those fatty acids transform. They lose a small fragment and become alkanes, one carbon shorter, but still carrying the chemical fingerprint of what they once were. The alkanes Curiosity found in Cumberland were 10, 11, and 12 carbons long. That matches precisely what you would expect from the degradation of early microbial membrane chemistry on Earth. This is not a forced fit. The match between what organisms on early Earth produced, what chemical degradation predicts, and what Curiosity found is the kind of alignment that makes careful scientists write papers about hypotheses they would normally treat with much more caution. A Martian biosphere at this time would not have been large or dramatic. A thin microbial mat at the bottom of a shallow lake, populations of cells cycling sulfur and iron through the sediment. Nothing visible from orbit, nothing that would have changed how the planet appeared from space. But life does not need to be visible to be real. Life needs to be alive. In ancient Gale crater, at the same moment life was establishing itself in the shallow seas of early Earth, those conditions were present, confirmed, and now chemically marked in the rock record. That parallel is what gives scientists hope. 2 planets, same moment, same chemistry, one known to have produced life, one now holding molecules that fit the same pattern. Understanding what ended that world is the next piece of this story. And understanding what ended that world, the sequence of catastrophes that stripped away the conditions for surface life on Mars, is the next piece of this story. Because the death of a planet's habitability is not a quiet event, it is one of the most violent planetary transformations in the known solar system, and the timeline of that destruction matters for what, if anything, could have survived it. If life existed on early Mars, something ended it. Mars underwent a transformation so severe that any surface or near-surface biology would have faced a series of extinction-level pressures over roughly 1 billion years. Understanding what those pressures were helps us understand what might be preserved in the rock record, and whether anything could have found a way to persist. The first blow was the loss of the magnetic field. Roughly 4 billion years ago, Mars's internal engine shut down. Earth has a spinning liquid metal core deep inside, generating an invisible magnetic shield that deflects high-energy particles from space. That shield is why life on Earth's surface can exist at all. Mars lost its equivalent of that shield. Confirmed fact: no magnetic protection, full exposure to solar wind and cosmic radiation. The second blow was atmospheric loss. Without a magnetic shield, charged particles from our star began slowly stripping away the Martian atmosphere. Particle by particle, molecule by molecule, over hundreds of millions of years. The atmospheric pressure dropped from potentially Earth-like levels to less than 1% of what Earth has today. Multiple independent measurements confirm this happened. As the atmosphere thinned, surface liquid water became physically impossible. Water either froze solid or escaped to space. The lakes dried. Gale crater became what it is today, a chemical fossil rich in preserved history, completely silent in terms of active chemistry. The third blow was chemical starvation. Without liquid water, the reactions that chemolithotrophic microbes depend on for energy slow to nearly nothing. The mineral water gradients they exploit for food collapse. Any life dependent on aquatic surface environments would have faced starvation alongside radiation and cold. But here is where the science gets genuinely interesting. The transition was not instantaneous. Evidence suggests Mars may have had episodic liquid water on its surface as recently as 1 billion years ago. Some researchers believe that deep subsurface environments, protected by kilometers of rock from radiation and warmed by residual geological heat, could still hold liquid water pockets today. This is a theory, not confirmed, but on Earth, bacteria have been found alive in solid rock miles below the surface, living on chemical energy from water reacting with minerals, with no connection to the surface world at all. The deep rock biosphere on Earth is vast and ancient. Whether Mars has anything like that today is a genuine unknown mystery. The surface is a wasteland. The deep interior has never been properly explored. Whatever happened to life on early Mars, if it existed, was not sudden. It was a slow, relentless suffocation over millions of years, and the evidence of what was there before that process began may be exactly what's sitting in Cumberland. But before we accept that conclusion, there is one more challenge to address directly. Every time organic molecules are found on Mars, the same question appears immediately. Could it be from Earth? Could the molecules in Cumberland have been carried to Mars on the rover, introduced during manufacturing, assembly, or the journey through space? This is the right question. Every serious scientist asks it first, and the team addressed it carefully, because without a careful answer, the entire finding collapses. Curiosity was built in a clean room. Its instruments were assembled under strict protocols designed to minimize organic contamination. Before launch, every component was checked for organic residues. The chemistry lab was baked at high temperatures to drive off any absorbed organics. The cleaning procedures used on Mars missions are among the most rigorous in any manufacturing environment on Earth. But no process is perfect. The question is whether the signal from Cumberland could plausibly be explained as contamination rather than Martian chemistry. The team had several lines of evidence arguing against that. First, the amount. 30 to 50 parts per billion is not a trace contaminant level. Documented contamination from manufacturing and assembly typically appears at parts per trillion or lower in controlled analyses. The Cumberland signal is orders of magnitude above background contamination levels for this class of molecules. Second, the location. The molecules were found inside a rock sample. Curiosity drills into rock and analyzes powder from the interior, material that has been sealed from the surface environment for billions of years and sealed from the rover's exterior by solid rock. Contamination from the rover's outer surfaces cannot penetrate sealed mudstone. Third, the distribution pattern. If the signal were contamination, you would expect similar profiles across multiple sample types and locations, since the same rover drilled all of them. The long-chain alkane signal in Cumberland rises significantly above what other sample sites show, in ways consistent with local geology rather than a uniform source. Fourth, the blank experiments. The chemistry lab routinely runs blank analyses using empty sample cups to characterize its own background contamination. The Cumberland signal clearly rises above those blanks. Contamination cannot be ruled out with absolute certainty in any space mission. That is a scientific reality, but the evidence argues strongly against it as the explanation here. The signal is real. It is inside the rock. It behaves like Martian chemistry. That actually makes the situation more significant, not less. Because if contamination cannot explain it, and every other non-biological option has either failed the math or cannot be quantified, the remaining explanations narrow to a very specific point. And there is one test that could cut through all the remaining uncertainty in a single measurement. A test so precise, it has settled debates about life in rocks 3 billion years old. It has not been run on Cumberland yet, and understanding exactly why reveals everything about where the search currently stands. There is one measurement that could give a near-definitive answer. It has not been made, not because scientists do not want to make it, but because it cannot be made with any instrument currently operating on Mars, and understanding why reveals exactly where this entire investigation stands right now. The measurement is called compound-specific isotope analysis. Here is the idea, as simply as possible. All carbon comes in two slightly different versions, mostly carbon-12 and carbon-13. These behave identically in everyday chemistry, but living things prefer the lighter version when building their molecules. That preference, consistent across all life on Earth, leaves a measurable fingerprint in biological molecules that survives in rock for billions of years. A deeply negative reading from this measurement indicates biological production. A reading near zero argues strongly against it. Scientists have used this exact approach to verify biological material in Earth rocks over 3 billion years old. It is reliable, it is well understood, it is one of the gold standard tests in geochemistry. For the Cumberland molecules, this measurement could give a clear answer: biological origin or not. The instrument required is completely standard in any Earth geochemistry laboratory, about the size of a kitchen appliance, used routinely. Getting it to Mars, operating it in Martian conditions, and running it on a specific set of target molecules is a different matter entirely. The chemistry lab on Curiosity can measure carbon isotope ratios, but only in bulk, across a complex mixture of many compounds at once. Separating the specific isotope signal of the long-chain alkanes from everything else in the sample is beyond its capability. That level of separation requires isolating individual molecular compounds first, then measuring their isotope ratios separately. That cannot be done on a rover in current conditions. So the measurement that could settle this sits waiting in laboratories on Earth, and the samples that would give us the answer are sitting in tubes on the surface of Mars. This is why Mars sample return is not just a space mission, it is the linchpin of the entire investigation. Without it, the question stays open indefinitely, not because the science is insufficient, because the gap between the evidence and the tools to read it is 400 million miles wide. But there is actually an even more definitive test than this one. Something that would go beyond isotope ratios. Something that would remove almost all remaining scientific doubt in a single measurement. It comes down to a property of molecules that most people have never encountered. A property so fundamental to life on Earth that its presence or absence in Martian organics would be the strongest single piece of evidence ever collected in the search for life beyond our planet. But there is actually an even more definitive test than isotope analysis. Something that would go beyond carbon ratios entirely. Something that would remove almost all remaining scientific doubt in a single measurement. It comes down to a property of molecules that most people have never encountered, and if it can ever be measured in Martian rock, the result would settle the question as completely as science allows. There is something even more powerful than carbon isotopes. It is called chirality, molecular handedness, and if it can ever be measured in Martian organic molecules, the result would be as close to definitive proof as science allows. Here is the concept, explained simply. Many organic molecules can exist in two mirror image forms. Like your left and right hands, these forms are identical in almost every way except their spatial arrangement. Scientists call them left-handed and right-handed forms. In chemistry without life, whether in space, in laboratory reactions, or in geological processes, both forms are produced in roughly equal amounts, a 50-50 mix. This is the default state of organic chemistry whenever no biology is involved. Life breaks that balance completely. On Earth, all amino acids in living organisms are left-handed. All sugars are right-handed. Every living thing on Earth follows this rule without exception. Nobody fully understands why life locked onto these particular forms so early in its history. But the lock-in happened, and every organism inherits it. The consequence for the search is powerful. Find amino acids in ancient rock, measure the ratio of left-handed to right-handed forms, and you have an almost definitive answer. A 50-50 split means no biology was involved. A strongly one-sided ratio means biology was almost certainly there. Current instruments on Mars cannot measure this. Chirality analysis requires precise chemical separations that are sensitive to temperature, contamination, and environmental conditions that are very difficult to control on a rover operating on another planet. But prototype instruments have been built that could do exactly this in a Mars-compatible format. The European Space Agency developed one for their ExoMars rover known as the Rosalind Franklin mission, which has experienced repeated delays due to political and technical complications and had not launched as of early 2026. If that rover ever reaches the Martian surface, it would carry the most powerful biosignature detection instrument ever sent to another world. 2 tests, isotope ratios and molecular handedness, either one could tell us definitively what produced the Cumberland molecules. Both require either significantly better instruments on Mars or the return of samples to Earth. The search for life on Mars is not waiting for a discovery to be made. The discovery may already have been made. The search is waiting for the verification tools to arrive. And every year those tools do not arrive is a year the most important scientific question in human history goes unanswered. Not for lack of evidence, for lack of the instruments to read it. If the Cumberland molecules are biological, they almost certainly carry the signature of one-sided molecular handedness, built in at the moment they were first assembled in a living cell billions of years ago. 2 outcomes, 1 measurement, and we have not yet been able to run it. Step back from Mars for a moment. Everything the Cumberland finding demonstrates that complex organic molecules form in habitable environments, survive for billions of years in sedimentary rock, and exist in quantities that non-biological processes cannot explain, does not apply only to Mars. It applies to every world in the solar system with the right conditions, and there are more of them than most people realize. Enceladus is a moon of Saturn. It has a confirmed subsurface ocean of liquid water beneath its icy surface. It actively vents material into space through enormous geysers at its south pole. That material has been collected and analyzed. It contains organic molecules, hydrogen, carbon dioxide, and silica particles consistent with hydrothermal activity on the ocean floor. Scientists have identified over 100 distinct organic compounds in those geysers. Some are exactly the compounds associated with biological processes on Earth. This is confirmed. Europa is a moon of Jupiter. It has a subsurface ocean estimated at 2 to 3 times the total volume of all of Earth's oceans combined. That ocean is in contact with a rocky seafloor, potentially warmed by tidal forces from Jupiter's immense gravity. No mission has sampled its ocean yet, but the chemistry of Europa's surface suggests organic material is present, and the geological conditions match what scientists associate with habitability. Confirmed geology, unknown chemistry below the ice. Titan, Saturn's largest moon, has lakes and seas of liquid methane on its surface. Its atmosphere is rich in complex organic chemistry. Some researchers have proposed that if life exists on Titan, it would be chemically unlike anything on Earth, using liquid methane as a solvent rather than water. This is a theory, not confirmed, but the organic chemistry is extensive and real. What the Mars discovery adds to all of this is a precedent. Organic molecules in habitable planetary environments are common. The chemistry that could give rise to life appears distributed across the solar system. The question is no longer whether the ingredients for life exist elsewhere. They clearly do. The question is whether, given enough time and the right conditions, those ingredients reliably assemble into something that reproduces, evolves, and leaves a record behind. If Mars says yes, then Enceladus becomes urgent, Europa becomes urgent. The entire framework of the search expands from one hopeful case into a pattern demanding investigation. Scientists hope that Cumberland is not an anomaly. They hope it is a precedent, the first confirmed data point in what becomes a much larger story about how common life actually is in a universe full of the right ingredients. And that hope runs directly into one of the most unresolved problems in all of science. And that pattern creates a problem that physicists and philosophers have been wrestling with for over 70 years. If life is common, where is everyone? Why has nothing in the universe made itself known? The answer to that question is one of the most unresolved and deeply unsettling problems in all of science. And Cumberland just made it more urgent. If life began on Mars and Earth almost simultaneously, 400 million miles apart, why is the universe completely silent? This question has a name: the Fermi paradox. The gap between how common life seems to be and how utterly absent any signal from intelligent life is. And every piece of evidence suggesting life is common somewhere in the solar system makes that gap wider and harder to ignore. Physicist Enrico Fermi posed it in 1950. If intelligent civilizations are statistically likely in a universe this old and this large, some of them should have had enough time to colonize galaxies, or at least make their presence detectable. We should have found something. We have found nothing. Where is everybody? This seems distant from a mudstone in Gale crater. It is not. Because if microbial life is confirmed on ancient Mars, it significantly raises the estimated probability that life begins wherever conditions allow it. And if life begins readily, the complete absence of any signal from intelligent civilizations becomes much harder to explain away. Several serious possibilities have been proposed. One is that the gap between microbial life and intelligent, technologically capable life is enormous and involves transitions so improbable that they effectively happen only once per galaxy. Microbial life on Mars does not imply Mars ever produced complex animals, let alone civilizations. Earth took 3 billion years to move from bacteria to anything with a nervous system. That journey required specific, rare events that may not repeat easily. Another possibility is that intelligent civilizations are far more common than we can currently detect. Our search has covered a tiny fraction of the radio spectrum, from a small subset of stars, for only a few decades. Absence of evidence at this scale is genuinely weak evidence of absence. A third possibility is more unsettling: that civilizations like ours routinely reach a threshold where they cannot continue. A barrier so consistent that almost no species crosses it. If that barrier lies ahead of us rather than behind us, our current success tells us very little about our future. Mars cannot resolve the Fermi paradox, but it can tell us something critical about where in the chain from chemistry to life to intelligence the universe places its filters. If life begins easily, as Cumberland suggests it might, and the universe is still silent, then something is eliminating intelligent civilizations before they can be heard. That is a deeply uncomfortable thought, but scientists hope that the silence means something less final, that intelligence is simply rare, not doomed, and that Cumberland is evidence of abundance at the beginning of the chain, not a warning about its end. The rock in Gale crater is not just a chemical curiosity. It is a data point in a question that reaches all the way to the horizon of what matters. And that conclusion, if it turns out to be supported by confirmation of biology, changes the stakes of everything humanity does going forward, not just in space. For every decision we make about the long-term future of intelligent life in this part of the galaxy, the science is clear about what needs to happen next. The money is not following. Mars sample return has been ranked as the top large mission in planetary science by the National Academies of Sciences, Engineering, and Medicine. It has been supported by both the American Space Agency and the European Space Agency for over a decade. Hundreds of scientists across dozens of countries have agreed on it as the single most critical next step. It is also billions of dollars over budget, years behind schedule, and in the middle of a redesign process with no guaranteed outcome. This pattern is familiar in big science. The James Webb Space Telescope was originally projected to cost less than $1 billion and launch in 2011. It launched in 2021 and cost nearly $10 billion. Today, it is considered one of the most transformative scientific instruments ever built. The Cassini mission to Saturn faced multiple near cancellations before becoming one of the most productive planetary missions in history. But Mars sample return carries stakes that are different in kind. The samples Perseverance is collecting are not interchangeable with future samples. They represent specific geological contexts, specific moments in Martian history, documented with a level of scientific care that cannot be replicated. If those samples are not retrieved, they do not wait safely. They sit on the Martian surface, exposed to radiation and temperature swings, their scientific value slowly degrading year by year. The political reality is that space missions compete for funding against immediate priorities that always feel more urgent. The argument for spending $10 billion to retrieve rocks from another planet requires a public and a political class willing to take a genuinely long view, to invest in questions whose answers arrive after election cycles have turned over many times. This is hard in any era, but the timing of the Cumberland paper is deliberate. A peer-reviewed, agency-led study published in a major journal, finding that the best current explanation for ancient Martian chemistry points toward biology, released at the exact moment the mission to verify that hypothesis is fighting for its survival in budget negotiations, is not a quiet scientific development. It is an argument being made in public by scientists who understand that evidence changes political decisions. Scientists who hope that this particular paper, at this particular moment, tips the balance. The samples exist right now, sitting in tubes on another planet. What happens to this mission over the next few years will determine whether we get a definitive answer to the life question within a generation, or wait another 50 years. But even setting the mission aside entirely, there is something bigger being built here. A confirmation of ancient Martian life would not just answer one question, it would transform what kind of question we are allowed to ask next. And the next question is far more profound than whether microbes once lived in a Martian lake. Imagine the moment, not the press conference, not the headline. The actual moment when a scientist in a quiet laboratory looking at isotope data from a Martian rock sample sees a reading that is strongly biological and understands what it means. What changes? The first thing that changes is the scientific framework. Astrobiology, currently a field built on hypotheses and probabilities and careful maybes, becomes a field with a confirmed positive result. The entire structure shifts. Life is not unique to Earth. It arises wherever conditions allow. The universe, in some meaningful sense, is alive. That realization reframes every branch of science that touches on the question of origins. Chemistry, geology, biology, all of them acquire new context. The second thing that changes is philosophical. Every major human tradition, religious and secular, has a position, explicit or implied, on humanity's uniqueness in the cosmos. Confirmation of ancient Martian microbes does not threaten any particular faith. 3-billion-year-old organisms in a Martian lake are not competitors to any worldview, but the confirmation forces a genuine reckoning with ideas about cosmic significance, about what it means to be alive in a universe that contains other living things. That reckoning has been delayed for a long time. This would be the event that makes it unavoidable. The third change is practical. A confirmed biosphere in our solar system, even a long-dead one, provides evidence that life is a robust and repeatable outcome of planetary chemistry. That shifts the political and economic calculus of space exploration. It changes how we fund life detection instruments. It changes what missions get approved. Evidence of life transforms astrobiology from a speculative field into an empirical one. Funding follows evidence. Evidence changes everything. And there is a fourth change, perhaps the most important of all. Confirmation of past life on Mars would immediately raise the next question. Is it still alive? The surface is sterile, but deep beneath the radiation-blasted exterior, protected by kilometers of rock and potentially warmed by residual geological heat, isolated pockets of liquid water might still exist. Life that began in a warm lake 3 billion years ago and gradually retreated as conditions worsened could theoretically have found refuge in the deep rock. This is a theory. But on Earth, bacteria have been found alive in solid rock miles below the surface, with no connection to the surface biosphere at all. Confirmation of past life would not end the search. It would transform it into a completely different kind of search, more focused, more urgent, with a confirmed reason to hope there is something still to find. The generation responsible for finding that answer is already alive. The samples are already collected. The laboratories that could analyze them already exist. The only thing separating humanity from the most important scientific answer in its history is a decision about whether to follow through on the work that 2 rovers have already started. There are questions that matter more than the people asking them. Whether life exists beyond Earth is one of them. It has been asked by every civilization in recorded history, in every language, in every culture that has ever looked up at the sky and wondered. It does not belong to science, or to any space agency, or to any nation. It belongs to every person who has ever been alive. The generation alive right now is the first with a realistic chance of answering it. That is not an exaggeration. It is a straightforward assessment of the current technology, the current evidence, and the current trajectory of missions in development. Within the lifetimes of most people listening to this, humanity will almost certainly have data capable of definitively confirming or ruling out past life on Mars. If Mars sample return succeeds, if the right instruments reach the surface, if the samples come home and the analyses are run, the answer may be yes, the answer may be no. If the answer is no, if Mars turns out to have always been sterile all the way down, that tells us something profound. The origin of life is harder than we thought. The probability that we are genuinely alone in the observable universe increases significantly. Life on Earth becomes more improbable, more astonishing, and more precious than it already seemed. That is not a failure. That is an answer. If the answer is yes, if the isotope data or chirality measurements carry the unmistakable signature of biological production, every question about our place in the universe changes, not in a single dramatic moment, but in the slow, irreversible way that real scientific revisions work, as the implications spread through every field that touches questions of life and meaning and what the cosmos is actually doing. The responsibility of this generation is not to produce the right answer. The answer is whatever the evidence says. The responsibility is to actually look, to fund the missions, to build the instruments, to send the samples home, to do the work that earlier generations could not do because they lacked the technology, and that later generations cannot undo because the window of direct access to these specific samples in these specific conditions will eventually close. Scientists hope this generation chooses to look. They hope the funding comes through. They hope the samples come home. They have built the case as carefully and honestly as science allows. The rest is a decision that belongs to all of us. Cumberland has been waiting 3 billion years. The molecules are patient. The rock is patient. We are the ones who are not. And when the debate finally closes, when the measurement is made and the answer is recorded in the scientific literature for all time, the moment will belong to every person who ever looked up at a night sky and felt the weight of the question. It will not belong to any agency or government or institution. It will belong to the species that finally chose to look properly. We began with a drill. A small metal cylinder boring into grey mudstone at the bottom of an ancient Martian lake. A powder sample collected, sealed, and processed. A signal so faint it took 12 years and a different technique to find. What that signal revealed is not confirmation of life on Mars. Let's be precise, exactly the way the scientists were precise. Not confirmation, something subtler, and in some ways more important. The elimination of every convenient explanation. The narrowing of possibilities to a point where the biological hypothesis cannot be dismissed on scientific grounds. Before February 2026, the question of life on Mars was speculative. The evidence was interesting, worth investigating, but not yet at the level where the non-biological explanations had been systematically tested and found to fail. Scientists could reasonably say we simply did not know enough yet. That position had room to stand. After February 2026, that position is harder to hold. The team did not speculate. They calculated, they measured, they tested every alternative and documented exactly how each one failed. They published in peer review, where the work can be scrutinized, challenged, and either confirmed or refuted by the rest of the scientific world. The question has grown up. It is no longer asking whether Mars could have had life. It is asking what else could possibly explain what is in that rock. And based on everything currently known, the answer is nothing that anyone can fully quantify. That is not the same as proof. Science does not deal in proof. It works in probability, in elimination, in the slow accumulation of evidence that eventually makes the simplest remaining explanation impossible to ignore. We are not at the end of that accumulation, but we are much further along than we were. The debate that once belonged to science fiction has moved into peer-reviewed journals and budget negotiations and mission architectures. The question is no longer whether to keep looking. It is how fast we can get the tools to look properly. Scientists hope their discovery is a new beginning, not just for the field of astrobiology, for the way humanity understands its place in the universe. That hope is grounded in chemistry, in math, in peer-reviewed data from 2 rovers on another planet. It is the most carefully built hope in the history of science. The rock is there. The molecules are there. The calculation is done. Somewhere in Gale crater, in a small grey hole in a mudstone that sat undisturbed for 3 billion years, the universe is still waiting patiently to be understood. And for the first time, we have the tools, the evidence, and the reason to hope that we are finally close enough to hear the answer. If this story moved you, share it with someone who deserves to know it exists.